Good evening everyone. Myself Dr. D.S. Raghuvanshi, Professor of Applied Physics, Sri Shankaracharya Technical Campus, Bhilai. Today I am going to deliver a lecture on topic magnetism under the course of Fundamentals of Engineering Physics. So let us start. My contents includes history of magnetism, magnetic field, magnetic flux, magnetic moment, direction of magnetic field, Lorentz force, magnetic induction, magnetic field strength, magnetization, permeability, susceptibility, Biot-Savart law, Ampere's law, Faraday law, Lenz law, diamagnetism, paramagnetism, ferromagnetism and applications. Introduction. Magnetism is the force exerted by the magnets when they attract or repel each other. Magnetism is caused by the motion of electric charges. Every substance is made up of tiny units called atoms. Each atom has electrons, particles that carry electric charges. History of magnetism. A famous physicist, Hans Christian Ørsted, 1777 to 1851, a Danish physicist and chemist professor, he observed that a compass needle suffers a deflection when placed near a wire carrying an electric current. This discovery gave the first empirical evidence of a connection between electric and magnetic phenomena. Another famous physicist, Hendrik Lorentz, 1853 to 1928, a Dutch theoretical physicist, he investigated the relationship between the electricity, mechanism and mechanics in order to explain the observed effect of magnetic field on emitters of light, Zeeman effect. He postulated the existence of electric charges in the atom, for which he was awarded the Nobel Prize in 1902. Another physicist, Ampere's, was a French physicist, mathematician and chemist who founded the science of electrodynamics. Ampere's derived the significance of Ørsted discovery. He carried out a large series of experiments to explore the relationship between the current, electricity and magnetism. These investigations culminated in 1827 with the publication of the mathematical theory of electrodynamics phenomena deduced from experiments. Michael Faraday. In 1831, Michael Faraday made one of the most fundamental discovery. He established that a time varying magnetic field induces an EMF in a closed conducting loop. Faraday demonstrated electromagnetic induction for the first time by the warping two wires around opposite sides of an iron ring. One wire was connected to a battery that gave rise to a current and the other wire to a galvanometer. The current in the first wire generated a magnetic field which passed through the second wire. When the magnetic flux changed, a current was induced in the second wire as detected by the galvanometer. Magnetic field. When the electric charges are stationary, only the electrostatic interaction appears between them. When they are moving, an additional interaction appears between them. This additional force is called the magnetic force. The field by which the magnetic interaction occurs is called the magnetic field. The magnetic field is characterized by magnetic induction vector capital B. A magnetic field is always the result of moving charges and act only on the moving charges. When we shall note here the important difference between electric and magnetic force. First, the electric force acts always in the direction of the electric field, while the magnetic force is always perpendicular to the magnetic field. Second, the electric force does not depend on the velocity of the charged particle. It is the same whether the charged particle is moving or at rest. In contrast, the magnetic force acts on a charged particle only when it is in motion, and the force increases with the increases in speed of the particle. What is the magnetic field? A magnetic field is an invisible force field generated by a magnet like a bar magnet, horseshoe magnet, moving electric charge like a current carrying wire, toroid, solenoid, spinning electrons and changing electric field. The force due to a magnetic field is called magnetic force. The force can be detected in the presence of the magnetic substance. The magnetic field can exist in the air or vacuum. What does a magnetic field look like? A magnetic field can be pictorially presented by line typically drawn around either a magnet or a magnetized object. These lines are known as magnetic field lines or magnetic lines of force. As the magnetic field is a vector quantity, it has both magnitude and direction. The number of lines passing through a given surface is called the magnetic flux. The flux per unit area perpendicular to the direction of the line is called the magnetic flux density, which gives the strength or magnitude of the magnetic field. A line drawn tangentially at any point on the field line gives the magnetic field direction. The magnetic field lines are analogous to electric field lines. Field lines in a bar magnet. A bar magnet is the simplest form of a magnet that is a rectangular. It has two poles called the north pole and the south pole. The magnetic field line come out of the north pole and terminate into the south pole. Inside the magnet, they travel from south to north pole. The magnetic field line can be sketched by bringing a compass near to the magnet. The compass aligns along these lines and the needle point toward the direction of the magnetic force. When two bar magnets are brought closer, the magnetic field will be destroyed. In this case, opposite poles attract and similar poles repel. Direction of the magnetic field. The right hand rule gives the direction of the magnetic field. According to this rule, the thumb indicated the current direction. The fingers curling around the conductor indicate the magnetic field direction. Just like a wire direction of the current and finger represent the direction of magnetic field. And equation V equal to mu naught I upon 2 pi r. What is the magnetic flux? Magnets and electromagnets produce a magnetic field represented by imaginary lines like as magnetic field line or magnetic force line of force. Magnetic flux is the number of lines passing through a given area, whether is air or vacuum or inside a magnetic material. The magnetic flux is analogous to the electric flux. The magnetic flux phi is given by the dot product of the magnetic field and the area vector phi equal to B dot A. If the angle between the magnetic field vector and the area vector is theta, then the magnetic flux is given by phi equal to B A cos theta. SI unit Weber or WB. When theta equal to 0, then cos 0 equal to 1. Then phi equal to V into A. Therefore, the flux is maximum when the area under the consideration is perpendicular to the magnetic field. Magnetic moment is a measure of the strength and orientation of a magnet. Magnetic field, it is a vector quantity characterized by both magnitude and direction. Magnetic moment mu is defined as mu equal to I into A, where mu is a magnetic moment, I is the current, A is the area of current loop. The unit of magnetic moment is ampere square meter. For a bar magnet, the magnetic moment is mu equal to m into small l, where m is the magnetic moment, mu is the magnetic moment, m is the pole strength, I is the distance between the poles. Magnetic moment is a fundamental property of magnets and is used to describe their behavior in various situations such as magnetic field, torque, rotation, energy, work, etc. The origin of magnetic moments. The magnetic moments come both from the electrons orbiting an nucleus and its spin. The most fundamental magnetic moments is the Bohr magnetron mu b equal to 9.27 into 10 raised to minus 24 ampere meter square. Next is orbital electrons is atom is a current loop and has a magnetic moment in a mathematical form I equal to q upon t and t equal to 2 pi upon omega. They put the value of I equal to e omega upon 2 pi and mu orbital equal to I into pi r square equal to area and then equal to minus e omega r square upon 2 minus sign for electrons. Since angular momentum L of the electrons is L equal to mvr equal to put the value of v and m omega r square, put the value of momentum equal to minus e upon 2m into L. The ratio e upon 2m equal to gyromagnetic ratio. Minus sign indicate momentum is in opposite direction of angular momentum L. Direction of magnetic field and Maxwell right hand rules. The direction of suppose the current, the thumb represent the direction of current in wire and finger curl is direction of the magnetic field. If it is the opposite, the direction of magnetic field and direction of current. Fleming left hand rules. The middle finger represent a current or velocities and for this finger is represent the field magnetic field direction and thumb is direction of the force. Lorentz force. A charged particle moving through a magnetic field of strength V with a speed small v will feel a Lorentz force with a magnitude of F equal to q v b sin theta, where theta is the angle between the velocity of the particle and the magnetic field. Field line run from N to S and q is the charge of the particle. This force act as right angles to both the magnetic field and the velocity of the particle. The magnetic force does not have the same direction as V, it is always perpendicular to the both V and V. The above features of magnetic force may be summed up in a equation as follows: F equal to q bracket में V cross V, where the direction of F is perpendicular to V and B. This figure shown is the earth magnetic field. Earth magnetic field is the about 0.5 Gauss or 5 into 10 raised to minus 5 Tesla. Property of magnetism. In the context of magnetism, the symbols B, H and M represent different magnetic quantities. Here are their definitions. B, magnetic flux density, also known as magnetic inductance. It is unit is Tesla. Definition: the magnetic flux per unit area measured in Tesla. It represents the strength of the magnetic field. Formula: V equal to phi upon A, where phi is the magnetic flux and A is the area. Next H, magnetic field strength, also known as magnetization field, unit ampere per meter. Definition: the magnetic field strength measured in ampere per meter. It represents the force that produces the magnetic field. Formula: H equal to B upon mu, where B is the magnetic flux density and mu is permeability of the material. M, magnetizations, unit ampere per meter. Definition: the net magnetic moment per unit volume of a material measured in ampere per meter. It represents the magnetic properties of the materials itself. Formula: V equal to M equal to bracket में B minus mu naught H upon whole upon mu naught, where B is the magnetic flux density, H is the magnetic field strength and mu is the permeability of free space. Permeability unit Henry per meter H upon small m. Definition: the measure of how easily a magnetic field can pass through a material, or mu is a material property that describe how easily magnetic field can pass through it. Formula mu equal to V upon H, V equal to mu into H, where V is the magnetic flux density and H is the magnetic field strength. Permeability is a measure of the material ability to support magnetic fields. Mu naught is permeability of a free space, is a constant that represents the permeability of a vacuum. B and H are vectors, while M is the vector field. The relationship between B, H and M is given by the equation B equal to mu naught bracket में H plus M. Susceptibility, it is a dimensionless unit. Definition: the measure of how much a material is magnetized when exposed to a magnetic field. Formula: chi equal to m upon h, या m equal to chi into h, या m is direct proportional to h, chi is a proportionally constant, where m is a magnetization and h is the magnetic field strength. Susceptibility is a measure of the material's response to magnetic fields. Relationship between permeability and susceptibility: mu equal to mu naught bracket में 1 plus chi, where mu naught is the permeability of free space, chi equal to mu upon mu naught minus 1, or mu r equal to 1 plus chi. In other words, permeability is the sum of the permeability of free space and the susceptibility of the material. Weier's-Savart law. The Weier's-Savart law is a scientific principle that describes the magnetic field generated by small elements of electric current. It is a fundamental concept, is a understanding how magnetic field are create and behave. What is states? The Weier's-Savart law states that the magnetic field dB created by the small elements of current I bracket में ds is a proportional to the current elements I, the length of the current elements ds, the sine of the angle theta between the current elements and the position vector r, inversely proportional to the square of the distance r between the current elements and the point where the magnetic field is being measured. Mathematical formula: dB equal to mu naught into I into ds cross r upon 4 pi r q, where dB is the magnetic field, mu naught is the magnetic constant या permeability of free space, I is the current, ds is the length of the current elements, r is the distance between the current elements and the point where the magnetic field is being measured. Theta is the angle between the current elements and the position vector r. And other diagrams, the Weier's-Savart law for a small magnetic field produced by the current in the wire, dB equal to mu naught upon 4 pi I ds cross r cap upon r square. In term of out magnetic field and magnetic field, out magnetic field represented by P and P dash, and then total magnetic field B equal to mu naught I upon 4 pi integral ds cross r cap upon r square. Definition: what is the Ampere's law? Ampere's law or Ampere circuit law is a mathematical statements used in electromagnetic that gives a relationship between a current and magnetic field. It generates the magnetic field produced by an electric current is proportional to the magnitude of the current with a proportionality constant equal to the permeability of a free space mu naught, a universal constant in physics. Its value is 4 pi into 10 raised to minus 7 Henry per meter. It in its discrete form, Ampere's law states that for any closed path, the sum of the length elements times the magnetic field in the direction of the length elements is equal to the permeability times the electric current enclosed in the loop. Ampere's law can be expressed in both integral and differential form. The integral form is generally used to determine the magnetic field, and the magnetic field is derived from Biot-Savart law will yield the same results. This is shown the both form, integral form integration b dot dl equal to mu naught into I, and differential form del cross b equal to mu naught into j. I is electric current, B is the magnetic field, mu naught is the permeability of free space, J is current density and direction of current in right hand thumb rules. And application of Ampere's law. Ampere's law has a many practical applications. The primary use is of course calculating the magnetic field generated by an electric currents. This law is useful in the electromagnets, motors, generators and transformers. Limitations of Ampere's law. The primary limitations of Ampere's law is that it is applicable in a magnetostatics and is valid for the steady current, that is the electric field does not change with time. However, the Maxwell modified Ampere's law by the introduced displacement current. It is the quantity del d upon del t appearing in Maxwell equation and is defined in the term of the rate of change of d, the electric displacement field. Maxwell added this term of the electric current term in Ampere's law and used the amendment version to derive the electromagnetic wave equation, which form the basis for Maxwell equations. Faraday law. What is the Faraday law? Faraday's law of electromagnetic induced states that a voltage is induced in a conductor whenever relative motion exists between the conductor and an externally applied magnetic field. The magnitude of this voltage is proportionally to the rate of change of the magnetic flux. Thus the law establishes a quantitative relationship between the changing magnetic flux and the induced voltage in an electromagnetic circuit. Figure Faraday law and equation EMF equal to minus n d phi upon dt, epsilon EMF electromagnetic force and n number of turn of the coil, d phi upon dt instantaneous change of magnetic flux with time. Faraday law equations. Consider the example of the conducting wire wood into a coil. Suppose this coil is placed in an external magnetic field represented by magnetic lines of force. The number of lines passing through a given cross sectional area is defined as the magnetic flux. There are several ways to change this flux. According to the Faraday law, a change in the magnetic flux gives rise to an induced voltage called electromotive force EMF. Mathematically, this law is given by the following formula already explained. Application of Faraday law. Faraday law is one of the most fundamental law of electromagnetism. This law find its application in most electrical device. It can explain the working principle of the transformer, generators, inductors and motors. Here are a few uses and applications, including some in daily life. Generator, a device that convert mechanical energy into the electrical energy used in an external circuit. A conductor coil is rotated rapidly between the poles of a horseshoe type magnets. The rotating coil intercepts the magnetic field and a current is induced in it. Electrical bells, the device that a function using an electromagnet. Lenz's law. The electromagnetic induction is governed by the two fundamental laws, Faraday's law and Lenz's law. Faraday's law establishes a relationship between the induced EMF and the magnetic flux rate d phi upon dt in the conducting coil of n turns. It is given by the following formula: EMF equal to minus n d phi upon dt. However, this equation does not state anything about the conservation of energy. Lenz's law can be explain energy conservation, and the negative sign is the Faraday law equation. Lenz's law states the polarity of the induced EMF is such that is oppose the change in magnetic flux that produce it. The negative sign is because the induced EMF oppose the magnetic field. The magnitude of the EMF is given by the mod EMF equal to n d phi upon dt, where n equal to 1 and d phi upon dt equal to 1 Weber per second, then EMF equal to 1 volt. Therefore, the induced EMF is the voltage generated across the coil of 1 turn when the flux rate is 1 Weber per second. Lenz's law determines the direction of the induced current. When a magnetic field induces a current in a conducting coil, the induced current generates its magnetic field opposite to the inducing magnetic field. In other words, an induced current will always oppose the motion that started it in the first place. Lenz's law is significant since it can determine the direction of the induced current and the magnetic field induced by the current. The change in the magnetic flux around a conducting coil may be caused in several ways. Change the magnetic field strength, move the magnet toward or away from the coils, move the coils into or out of the magnetic fields, rotate the coils relative to the magnetic Lenz's law is named after German physicist Lenz after he deduced it in 1834. Diagrams for without no current in this loop and direction of the momentum and direction of induced current and opposite direction of momentum and induced current. So, here I would like to conclude my lecture. I hope you all have understood the concept of the magnetism and its application in real life. Thank you for watching. Thank you.